Here we're going to talk about stereoisomers of coordination complexes. So stereoisomers have the same atoms bonded to the metal, but there is a different arrangement of the atoms in space. And like all isomers, they have to have the same chemical formula, of course. There's two types of stereoisomers. There's diastereomers and enantiomers, and you're familiar with these from organic chemistry. Diastereomers are also called geometric isomers, and that may be a more common term when it comes to coordination complexes. And enantiomers are optical isomers. So we'll talk about geometric and optical isomers. Diastereomers, just like organic, can have very different chemical and physical properties. So here are some geometric isomers. There's cis and trans isomers found in square planar complexes, where you have two different types of ligands, two of each. And you can also get this in octahedral compounds, where you have 4 ligands of one type and 2 ligands of another. So here we have, this is cisplatin actually on the left-hand side, and it's a chemotherapy. And you have trans, and the trans version. So cis, remember, is same side, trans is opposite. So this is similar to the naming of alkenes, but of course has a slightly different meaning here. But when the chlorines, or whatever those two ligands are arranged on the same side, that's cis. If they are opposite each other, it's trans. And again, this is the square planar orientation. Here is the, when we're dealing with octahedral compounds, let's say we have ligand B, when they're next to each other, so 90 degrees to each other in octahedral complexes, that is cis. If they're 180 degrees from each other on the opposite sides, that would be trans. You can also have facial and meridional, which is FAC and MER. This is a little bit different than cis and trans, because now instead of having 4 ligands and 2 ligands, like in the cis and trans situation, you have 3 and 3. So if the 3 and 3, if you think of an octahedral compound, or octahedral shape, remember we call it, even though it has 6 vertices, it has 8 sides, and that's why we called it octahedral. It's an octahedron. So if one of those faces is all the same, is connected by all the same ligand, like in the right hand example, that's facial. So an entire face of that octahedron is one ligand type. So that's why we call it facial. And that's, again, FAC, F-A-C. Meridional is, if you think about something along the meridian, all of the same ligands are on the same plane, going through the metal center. So you have 2 that are 180 degrees from each other, and then one that's 90 degrees to both of those. So it's along a single plane, or a meridian of the of that structure. So these are the two different orientations for 2 types of ligands on an octahedral compound. So facial and meridional. This is another way to show that, facial versus meridional, when we're not showing an actual 3-dimensional representation, but when we're using dashed and solid lines, for example. You can still see the facial or FAC for the left hand, and you can also have that with tridentate ligands. So if you have 2 tridentate ligands like diene, you can have 2 of those, and you can still get kind of a facial or a meridional sort of setup with that. So it's not just for monodentate ligands. So that was geometric isomers. You can have optical isomers. That arises when a complex and its mirror image are not superimposable. So we're quite familiar with tetrahedral complexes, in which you have 4 distinct groups off of it. And you can have enantiomers, the mirror image. Again, remember from organic chemistry, we had designated them with R and S, for example. You can get this sort of thing, however, with bidentate ligands as well. And there's other examples of optical isomers here. Sometimes you'll hear like lambda or delta isomers and that sort of thing. And that would be situations more along these lines. So, for example, ruthenium, when it has 3 ethylene diamines on it, you can still have 2 enantiomers that are mirror images of each other there actually. So you do end up getting this with some bidentate or multidentate ligands. It's okay for us to just talk about them as enantiomers, and oftentimes we're not really distinguishing between these anyhow. But if you ever see that lambda versus delta, that would be some situations like this ruthenium ethylene diamine, for example. So that's it with regards to stereoisomers. Yeah, so here is the entire Coordination Chemistry 1 structures and isomers. So we went through the background and history, notably Werner. We surveyed ligands and different binding types, so monodentate and all of those sorts of things. Also, things along the lines of like macrocycle effect and chelation. Then we had coordination numbers and structures, and a lot of that is similar to stuff that we've dealt with in the past in terms of geometries. Then we did naming these complex ions or inorganic and coordination compounds. Talked about structural isomers, notably linkage isomers in terms of being able to use hard-soft acid-base theory to predict the sort of linkage that you would expect. Then lastly, stereoisomers, which are along the lines of stuff that you've learned in the past, but now we have cis and trans and a couple different types of cis and trans, and facial and meridional, for example.